right, in section 4.2, we learn that we're going to be working with systems of equations, and what a system of equation is just basically two or more equations, and we put them on the same graph, and where they all intersect is the solution. Most of the time, we're going to have just two equations at a time. So before we get into solving some, I wanted to talk about the different kinds of things that can happen when we solve. Let's say I have an x and y coordinate grid, and I graph two things, and I see that I got two lines. I'll make one line green and one line blue. Where they cross is the solution. So the solution in this case, these two lines cross in a point. So there's one solution, and it is a point. Remember, a point has two parts. It has an x part and a y part. Okay, that's supposed to be a comma. I just can't quite get it to accept what I want it to do here on the iPad. Okay, so when we have one point, we have a label that we call that when we have graphs that cross in one point. And that's one solution. We call that independent system of equations. Independent, I misspelled it. System. Okay? And when we solve, we'll get an x value or a y value, and then we'll have to take that value we find and we'll plug it in and find the other part of the solution. Well, there's a couple of other things that can happen. Sometimes when we have lines and we graph them, I know that's a horrible coordinate system, but let's say we graph two lines, we'll go ahead and use it anyway, and they're parallel. How many places do parallel lines cross? Well, they don't, do they? They don't cross. There are no solutions for parallel lines because the solutions are the points they have in common, which on the graph is where those two lines would intersect. And since they don't intersect, there are no solutions. So no solutions, when that happens, we say that is an inconsistent system of equation. I already misspelled that one too. This inconsistent system. This is all on page 116 if you're looking for it. So that's when there's no solutions. And if you think about parallel lines, they never cross, so there would be no solutions. Parallel lines are inconsistent with having a solution, so those are inconsistent systems. I'm not going to write the word system since it gets too cluttered here. There's a third thing that can happen. What if I graph a line? Here I go, I graph it. And then I come back behind it and graph the other line, and look what happens. It lays right on, let's say it's laying right on top of the first one. They are, in effect, they are the same line. Sometimes we find out that two equations represent the same line. Maybe we don't recognize it because they've tried to disguise it by multiplying through with a fraction and a negative number or something. Well, how many places do those two lines cross if they're one right on top of each other? Well, they cross at every single point on the line, and there are infinite points on the line, so there are infinite solutions. Infinite solutions. No matter what x I pick, there's a solution on that line because I can find a point on the line, which is really two lines on top of each other, right? But the same line. So when there's a label for that kind of system of equation, and it's called dependent. The lines are the same. They are so tight with each other. They are so close to each other. They are dependent systems of equations. Now we're going to find with this inconsistent and dependent, there's some things that happen algebraically that let us know we got that kind of equation. So we're going to look at those, and I'm going to work some problems from the lesson today. I tried to make a video in class, didn't go well, so we're making some more, here just to try examples. I'm going to pick some different ones than we did in class just so, we can have some more examples. So let me say, I'm going to pick number 8. We were doing the evens, okay? Number 8, the system of equations, the two equations are 3x plus 10y is equal to negative 24. And then 6x plus 7y is negative 9. If you remember from Algebra 1, when we had these systems of equations, there were 3 ways we had to solve them. We're going to focus on one way in this chapter 4 here. Some other ways is we try to solve for one variable in terms of the other variable and use something called substitution. We're not really working on that in this chapter. Another thing we could do is to graph the two equations and see, are they parallel, are they the same line, or do they cross in a point? We can check our work that way, but again, we're not going to work so much in this section doing that, okay, in this chapter. The way we're going to work is called linear combination. Linear combination, it has some other names. Sometimes books will call it adding equations. I'm going to write that in a different color. Adding equations. And the reason is because you add the equations to solve them. Other books call this elimination. These three different colors, three different terms here. But they all refer to the same thing. Now, when I add equations, the thing that I've got to have happen in order for it to be helpful at all is for one of the variables to go away. If I add these the way they are now, nothing's going to go away. I don't have 3x minus 3x would make the x's go away. If I added them, I'd have 3x plus 6x is 9x, 10y and 7y is 17y, and then I'd add my numbers. Not helpful. Nothing went away. What I'm trying to do is get rid of or eliminate one of the two variables so that I can find the other one, find what number it represents, and then go find the other part of the point. So that's what we're trying to do here. If I add them, it won't necessarily help me. So what I can do is this. I can change the equations. Sometimes I have to change one equation. Sometimes I have to change both of the equations. But here, let's decide first, do we want to get rid of x's or y's? I could get rid of either one of them. I'm going to choose x's just because I like the fact that the numbers are smaller, and these numbers are already big enough. I don't want to make them any bigger than they are. So here's the deal. If I want to get rid of the x's, I have a 6x on the bottom. I need to have 6x add to negative 6x to cancel out. Well, right now up on the top, I don't have negative 6x. I have 3x. I could get a negative 6 there, negative 6x, if I multiply through by negative 2. So what I'm going to do is multiply the whole top equation by negative 2. It's the same equation. We're just kind of giving it a little facelift to make the numbers more, easier to work with. But it'll still be the same equation. Negative 2 times 3x is negative 6x. Negative 2 times 10y is negative 20y, and I've already let me try to fix that. Okay. And then negative 2 times negative 24 would be a positive 48. So I just changed my first equation. Now, I don't have to change my second equation because I made it be able to cancel out without doing something to the second equation. Sometimes I have to do something to both, and we'll do some examples of that. So negative 6x and 6x, if I add that up, that's 0, which I usually don't write down because it's just going to be 0. Now, negative 20y plus 7y would be negative 13y, and 48 minus 9 would be 39. So now I've got this little equation, and I can solve it and find out what y is. Do you see why we want to get rid of one of the variables? It's so that we can find out what the other one is. And again, I could have picked either one to get rid of. It's just in this case, I thought it might be easier to get rid of the x's. All right, if I want to know what y is, how do I get rid of the negative 13 that's multiplied by the y? Well, the opposite of multiplying y by negative 13 is dividing it by negative 13. And if I do it to one side, I got to do it to the other. I get y is 39 divided by negative 13 is negative 3. Yay, that's a nice number. Some of these don't work out so nice, okay? So now I know that y is negative 3. So my answer, I can tell already, is going to be a point because I just found part of my point. The part of my point I found is the y part, which is the second part, right? The x's go first and the y's. So now I need to know what the x's are. In order to find the x's, what I'm going to do is I'm going to take this y value of negative 3 and I'm going to go up and I'm going to pick one of the equations and plug it in and solve for the x because that's what I don't have. I could pick either one I wanted to. I'm going to pick this bottom one just because I don't have as much junk drawn around it, so it's easier to see. All right, so let's say I pick that bottom one, 6x plus 7y, but I now know that y is negative 3 is equal to negative 9. So that's 6x minus 21 is negative 9. Okay, I'm going to try to cram this in here just so bear with the mess that's going to get created here. If I have 6x minus 21 is negative 9, and I'm trying to solve here, I could add 21 to each side. That would be 6x. 21 minus 9 would be 12. Yay, because if I want to know what x is, I divide both sides by 6, and x equal 2. Oh, my solution to the system is 2, -3. That means if I graphed them, they would both have this point on their graphs. They would cross at the point 2, -3. If I plugged 2, -3 into both equations, they would make true, both of them would be true statements. That's what it means for this to be a solution. So this is what we're going to do most of the time, and a lot of ours are going to, most of ours are going to come out with a solution like this, but not always. So we're going to look at some, and it'll probably be on a different video since this was getting long. We'll look at some that maybe end up with no solutions or infinite solutions, so that we can, talk about the things that we put earlier on the video. By the way, since this one has one solution, this is an independent system. It crosses in one point. So we would classify this as an independent system.